All right, good evening, everyone. So if you were planning to attend the joint meetup between Paris Women in Machine Learning and Data Science and Dresden Women in Machine Learning and Data Science, you are in the right place. We will start this meeting. This meeting is being recorded and will be available on YouTube. So yes, let me start with an online code of conduct before I introduce a bit the meeting. So the idea is to please make sure to save bandwidth, to switch off the video when you're not presenting, and mute your microphone when you're not talking. Of course, if you're asked to speak because you've raised your hand to ask a question, for instance, of course, unmute yourself. So yeah, if you want to ask a question, please use a chat or raise your hand. And if we get disconnected, no worries, we'll just all calmly reconnect to the Zoom. All right, I'm so happy to meet you again. We have this online version of the meetups. It's not the same as meeting in person, but on the other hand, it allows us to do those joint meetups between two different cities, so that's pretty cool. All right, in case you don't know, WiMLDS, Women in Machine Learning and Data Science, it's an organization whose mission is to support and promote women and gender minorities who are practicing, studying, or interested in machine learning and data science. WiMLDS has over 50,000 members worldwide, over 90 chapters in 30 different countries, a bit more actually, so including Germany and France. So a word of code of conduct. So WiMLDS is dedicated to providing a harassment-free experience for everyone. So we do not tolerate harassments. So please make comments that are appropriate for professional audience. Do not use sexual language and imagery, and most importantly, be kind to others. I think if you remember to be kind to others, that will cover everything in the code of conduct. So thanks for your help in this and for helping us make WiMLDS a welcoming and friendly community for all. So tonight's agenda, what's on our plate? Introduction by WiMLDS Paris. This is what is currently happening. And then there'll be a short presentation of WiMLDS Dresden before we move on to two talks, one by Sandra Lorenz, who is a researcher at the Helmholtz, who will talk about data science and machine learning and sustainable mineral exploration. And the other by Anastasia Lieva, who will talk about extreme data science. And then we'll have a bit more time for questions. Okay, so I'm here introducing WiMLDS Paris. So I'm Chloe, we are 4 members all here tonight with Marie, Caroline, and Nathalie. We were founded in 2017, and we are the 3rd largest chapter of WiMLDS in the world. We currently have over 4,000 members on Meetup, 2,000 followers on Twitter, 1,500 followers on LinkedIn. And it's for us, plus some volunteers who help us for different aspects of our activities. As I've already introduced the speakers, one slide ago, so let me skip those 2 slides, although they're very good looking. I didn't make them. If you want to know more after this meetup and you want to stay in touch, there's plenty of way of doing that. You can email us, you can follow us on Twitter, whether Paris or Dresden, or the global WiMLDS community, LinkedIn, Instagram, Slack. We have a website, we have a calendar, and all the slides will be available online. And of course, we have a meetup. That's how you came here. All right, so let's get started. And if you want to tweet about this event, feel free to do so, of course. And you can tag us and especially use the WiMLDS online hashtag. All right, so with this, I will step away and stop sharing and let people from WiMLDS Dresden present. So I don't know if it's Shima or Sarah who's talking. But the floor is yours.
Sorry, I was muted. So hello everybody. Also welcome from our side.
Shima, I can't hear you.
Oh.
I can actually hear you.
Can you hear me now?
We can hear you, yes.
Okay, great. So yeah, hello everybody. Welcome also from our side to this special event on this special month of Women's History Month. We are very happy to see these many attendees today. So let me just share my screen. Can you see my screen right now?
Yes, we can.
Okay, great. So let me introduce our team. My name is Shima. I'm one of the co-organizers of the Dresden chapter. I'm a researcher in this area. And our other wonderful co-organizers, Nadine Naumann, who is unfortunately not here in this event. She's an IT expert in a large company based in Dresden. And our other co-organizer, Sarah, who is actually a data scientist in another big company based in Dresden. So before we move to the presentations, I would like to ask Sarah to say hello and also a few words about our past activities, but impressive, because we are a very small community of around 116 people in Dresden. Sarah, stage is yours.
Thank you. Hello, everyone. Nice to meet you. Yes, as Shima said, I give you a very short overview of our past activities of the Dresden chapter. So our Dresden chapter was founded back in 2019, which is also when we had our first meetup, which was hosted by a local company, I4BD. And there we had two very interesting talks. And also in 2019, we participated in the diversity management working group of Silicon Saxony, which is a local high-tech network. In 2020, of course, due to Corona, we decided to switch to virtual meetups. And we then had a virtual meetup in the form of a data science panel discussion. We also co-hosted another virtual machine event together with Silicon Saxony and another meetup group here in Dresden, which is Machine Learning Dresden. Yes, now, of course, we are looking forward to having more meetups, of course, for now, virtual, and other activities here in Dresden. And we hope to see you there sometime. Thank you.
Yeah, thanks a lot. So if you have any concerns, questions about our small community, we are there for you. Please write to us or reach us in Twitter or in the Meetup page. And yes, so we are happy to be here today. I would like to pass to the first speaker, Sandra. So Sandra, stage is yours. Would you like to start?
Hello, thanks. I just will quickly share my screen. Okay, a band, and the cameras that we are using, they extend this a bit. So for example, if the cheaper versions of them, they would be a multispectral image, meaning so that they add a bit more to these bands. And on the bottom, you can also see how this then already increases the amount of information that you get. And then you can bring that up to a so-called hyperspectral image. And a hyperspectral image adds hundreds of contiguous bands that if you have a look at one specific data point, they provide you with the full reflectance spectrum for each of these points. So you can imagine that this brings quite a lot of challenges in regards to how to process, how to correct, how to interpret these data, how to bring them together with other data sets. And yeah, I just put here together a little word cloud of all the major phrases that we are usually dealing with. And of course, I cannot cover everything today, but just to give you a little overview on the versatility of that. So yeah, I would like to show you some of the aspects of this technique and how that can help to make mineral exploration more sustainable. And I would like to start with one of the major problems. So in the beginning, I already told you that mineral exploration is often done using this drill core. So basically, you make a hole in the earth and you extract these rock cones. And usually there's kilometers of these cores, and you get hundreds and thousands of these core boxes. And the normal approach would be that the geologist visits each of these boxes, logs them by hand, finds out which minerals there are, and notes them down and tries to delimit where the mineralizations or where your valuable materials are located. You can imagine that this is a huge work and really timely and costly, and a lot of bias is also included regarding the geologist that does this job. So what we are doing is so-called hyperspectral drill core scanning. So what you can see in the middle, we have a device that features several of these hyperspectral cameras, and that is able to scan these boxes, roughly 1 box per minute. And that creates a data set a spectral data set out of it. And here, if you remember the spectral ranges I showed you before, you can see how one of these drill core boxes, so you can see here roughly 3 meters of core, how these boxes or how these different spectral ranges show completely different spectra and completely different features throughout these different spectral ranges. And how important it is to also combine and integrate these different wavelength ranges. So there are, of course, a lot of different approaches that we can use to do that. But one would be, just presented that here quickly, that you take these hyperspectral data cubes and you break down the dimensionality of them and extract use feature extraction, either manual or automatic one, to gain some insights on the data specifics, and use that together with test and training points to do a supervised classification, to map your mineral classes, your mineral domains, and to separate basically in the end the valuable minerals from the non-valuable ones. So here I would like to show you in a little animation. I hope that is working. How this would look like. So here basically you see an RGB image of one of these drill core boxes, and after automatic processing and extraction of mineral features, you can already see how different minerals light up in different colors, and then we can in this specific case, we can map a mineral that is containing lithium, which is a very valuable element at the moment for battery technology, and which would have been quite difficult to map just by a visible eye. And then you can, of course, think that this one box will not help you a lot if you have 100 of boxes. So a large challenge that needs to be solved is to bring that first in to speed that processing quite up. So we implemented a kind of a real-time processing for that, and also to do that for hundreds of boxes at once. And you can nicely see how in the end, you can go from these quite dull looking cores to really a valuable map that shows you where which mineral is abundant, where your valuable materials are located. And you can even, together with the logging of the cores, you can localize them in 3D, and you can see how your valuable minerals are distributed into the ground. Yeah, so now I want to take you a bit out of the core shack and out of the subsurface and show you a different aspect of the hyperspectral mapping, and that would be the creation of digital outcrops and open mine pit mapping. So you can see us here in action. It's actually me on the right side, where we apply some of these hyperspectral sensors. You can see this the camera on the tripod in the middle, and one of a larger open mine pit. You can already see that, of course, this equipment also needs to be adapted quite well to the conditions that these mining environments bring with them. And the amount of cables, you can see that usually that's not quite yet the case. But yeah, that's why we are still doing research. Yeah, and what you would get in the end is something like you can see on the left side, which is a 2D spectral image. But what I want to show you here is how important it is to bring the full thing, to bring this picture, not only to see it as a picture, but to bring it in a 3D environment. The problem with these 2D spectral images is that you usually can only see distorted spatial relations. So it is really hard to see if these points that seem adjacent to each other, if they are really related or if they might be several hundred meters away. But the problem is that if you want to use all the most common machine learning and deep learning methodology, that most of them are made to be used in a 2D image space. So what we wanted to do is to use the full potential of the data set and to bring it in 3D and to make AI and machine learning see also the world in 3D as it is, to avoid these occlusions, to make possible to include spatial and spectral features together, and to allow a better object detection and segmentation. But for that, a lot of development is required. Of course, some methods exist, but they are mostly not really made to deal with these large data sets and to include several multimodal data sets. But how would that look like in the end? So I can see it's a bit blurry, I'm sorry for that. You can bring together several of these 2D spectral scans and bring them together into these 3D point clouds, as they are called, by estimating the pose of the camera. You can project them into the 3D space and can finally use the spectral data in this point cloud to map again your valuable minerals or different lithologies, different materials. And you would get something like you can see on the right side, where you can really have a 3D digital twin of your geological outcrop that you can use, store, and integrate with every other data type that has a geographic referencing. Yeah, so to make it even a bit more complicated, we can also lift our sensor up in the air. One of the major directions of research that we are doing is bringing spectral imagery on a drone, on doing drone-based mapping, which we found especially useful for mapping remote and inaccessible areas while still retaining a very high resolution of the imagery that we are taking. And yeah, you can see on the left a little example on that, how this data would look like. You can, of course, also bring that into full 3D and cover way more larger areas than you would be able to do so with terrestrial scanners. Of course, that these very, very complicated and moving, fastly moving platforms bring also a lot of complications in regards to data processing and data corrections. I don't want to go into detail a lot here, but just to show you all the variety of problems that we are facing when we are using these drone-based platforms. So for example, on the top, you can see a common problem that you have this very shaky, very high frequency spatial movements and vibrations, which usually bring a problem when acquiring different data sets. And you can see that in the before and after picture, that usually the data features a lot of offsets because each of the data frames is taken at a different position than the others. So they usually need to be co-registered, and we use several computer vision methods for that. So for example, key point detection algorithms such as SIFT to bring these data back together where they should belong. Another problem, of course, is radiometric correction, so distortions within the data per se. And we did a huge work on that. I suppose really you can see on the left side how problematic it can be and how many factors are influencing the final spectral signature that you are seeing. So it could be shadows, it could be light that is reflected from clouds, from adjacent targets. And all these things, topographic effects, different illuminations, they really hinder sometimes to get a good signal. But with implementation of different spectral processing methodology, we are able to correct for that. And you can see on the right how that clearly changes the complete shape of the spectrum and how important it is to really do these corrections. So one very good example on how important these corrections are is the mapping of rare earth elements. These elements show a very specific spectral absorption feature, which is very tiny and very hard to miss, very easy to miss, and is usually quite often hidden in the noise of the data. And only if you do very, very good corrections and you're really doing that correctly, you could be able to map these minerals eventually. And last year we could finally demonstrate that this is working from a drone-borne platform. And you can see here in the map a drone acquired spectral imagery, and you can see in red and yellow mapped these rare earth elements. And this is a huge success, as we can really directly map these materials from a moving platform. Another, just to show you another example on where these platforms could be interesting is, for example, the environmental monitoring. It could be specific aspects. In this example, it is the mapping of acid mine drainage, which is a common problem next to lignite mines or other mines that feature an acid outflow. And using the drones and using in this example logistic regression, we could we were able to map the pH value of the water of these mine outflows. And you can see here that you have a confluence of two rivers, and we could nicely monitor the confluence of this low and a bit more normal pH waters and how the mixtures behave. And could, of course, validate that also with water chemical analysis and in situ measurements. To give you a little outlook on where that could go to in the future. So for now, when we use these platforms, we are still doing the surveys manually or doing them automatically, but using only one drone. And one of the little dreams that would make that whole thing a lot more suitable and versatile for real applications is to use drone swarms. And that is something where also a lot of automation and deep learning will come into place. So basically what we could do is use several drones that organize themselves, that find specific targets within a larger area, and can then decide on their own which methodology, which spectral sensors are to be applied, and how large the surveyed polygons should be. And all of that can happen completely independent from an operator that might not be able to reach that area. And that should be a perfect application for mining setups and everywhere where it is quite dangerous to go with a human operator. So to conclude a bit, so just to give you some of the main advantages of how AI and machine learning can help to improve mineral exploration and mining. I listed here some of the major points. So we can enhance the worker safety by automating processes. We can reduce mapping costs, reduce drilling, enhance the mapping accuracy, speed, and coverage, and also reduce ore waste and the processing effort of ores by pre-selecting the material better. And we can, as I showed you last, do the environment, do a constant monitoring of the environmental impact. Yeah, here a little animation to conclude the methodology. You can see here one of these point clouds that has been acquired over a larger open pit. You can see how the ground-based data is acquired. The drone-based data is added, which has a much higher resolution and can complement this ground-based data. Then we can extract the geological attributes out of the data. And then finally, we can use machine learning to do a domaining and a classification of the materials that are abundant in full, and everything is happening in full 3D. Yeah, and that's everything from my side. I thank you a lot for your attendance, for your attention. And if there are any questions, please feel free to ask.
So thank you very much, Sandra, for this talk. I think it was very interesting. Lots of interesting questions and interesting challenges ahead. So please, if you have any questions, please raise your hand or type your question in the chat. And while we're waiting for others to ask questions, I have one question on, so you showed us this real-time applications, which seem to involve quite a lot of, quite a lot of computations. And I was wondering, like, if you could tell us a bit more on how this is working. I mean, do you have a lot of, like, is there a lot of work in the background to make models that can then make predictions fast? And where are the models stored? How does it work?
Yeah, of course. Yeah, so we have spent quite a lot of time into that, and it's also research ongoing. But I think the main issue is that this data, as you can imagine, is incredibly huge. So you have a lot of really high dimensionality, and if you even add several sensors, it gets quite large quite easily. So the most important step is to first break down the data and reduce the dimensionality and extract what really matters for the later interpretation. That's what we usually do with different methods of feature extraction. So we either use unsupervised methods. So most simple would be just the PCA, but also using more advanced methods such as spatially constrained feature extraction, such like OTVCA. But it could be also something done more manually and more spectroscopy based. So for example, by extracting mineral maps based on these specific mineral features. So you can use, for example, band ratios, you can use spectral feature fitting, or you can map specific parts of a spectrum, for example, determine at which position an absorption is taking place, if that absorption is shifting. And the result of this information you can store only within 1, 2, or 3 bands. So that already breaks down your data to a much smaller part and speeds up also the processing a lot. And then we tried also to optimize a lot how we classify and how we segment the data. At the moment we do it mostly sometimes using decision trees. We also used SVM. But there's a lot of testing at the moment ongoing, because it's not quite easy and can explode your data time quite fast if you get some of these kilometers of core.
Thanks. So someone is asking me several questions in the chat actually, but one that is directly related is, can you tell us how long it takes to actually process all the data? If you can give us a sense of the time it takes.
So in that case, it is really done. So we implemented a little tool that, so as I told you, so one of the scans while you are scanning one of these drill core boxes takes roughly like 1 minute or 1 to 2 minutes putting and releasing the box. And in the meanwhile, while the scan was taken and the next one is prepared, the data is already processed onto a fast computing server. And there you can get the first results within the next 5 to 10 minutes, something like that. So while you are scanning, you can already get your first results. So it depends a bit on how much you want to go into detail with your analysis. And so these first results could be already like a classification or a segmented map. But usually it makes sense to go back to your course to check your results and to improve your results again, and then that can take then, of course, some days, weeks, but it is more related to the constant checking and trying out different methodologies. Yeah.
Yes, okay, thanks. There's another question from the chat, which is about like how sensitive is your machine learning model to, as you know, how tailored it is. Like, so does it work only if you have like a very sunny, very well lit image, and how sensitive it is to the variations in the weather and light conditions?
So that's a really good question. We have just developed a methodology to cope for topographic effects. So these that are usually occurring when you have quite sunny and bright days. And we found out that basically 50% of the data variation that you have is just due to these illumination changes. So they don't really give you any insights on the material type, but just on the more or less the weather conditions that you have. But we are able to remove that. So basically you need to calculate the illumination model and remove that from your data. And then when you get these so-called at target reflectance data, so which should be corrected for all your external influences, then the machine learning model should not have too large of a problem coping with that. But these corrections are really essential. So if you don't do that, they can fundamentally influence the result of your classification.
All right, thank you very much, Sandra. In the interest of time, I suggest we move on to our second talk, but we'll have more time at the end of the meetup if there are more questions. So if you can unshare, and then I would like to invite Anastasia Lieva to start sharing her screen and start with her presentation.
Yeah. So, can you hear me?
Very well.
Hello, everyone. Thank you very much for having me. So, just to briefly introduce myself, I'm currently working at Comwatt. So, it's a startup in smart energy management. We are located in Montpellier. It's the southern France. And I'm also organizing the meetups in Montpellier in big data and data science. I'm passionate about this and in general by science, and I'm interested in social justice initiatives. So it's a great honor for me to speak at this meetup because the organizers are doing an amazing job to make this community and this society more diverse place to be. So thank you for that. My talk will be about data science, but let me start with a story that has nothing to do with data science, at least not yet. So, once upon a time, a company had a massive product that aimed to replace a mass of several payload applications with a single system, powerful and efficient enough to support all parallel processing for tens or thousands of employees. But 3 years later, the system hadn't printed a single paycheck and no software release had been made since the beginning of the project. At this point, there was clearly a need for a hero to break the curse of this project, so the company hired a hero. He analyzed the situation and he noticed some bewitched links in the chain of the whole process. The first one was a habit where a client gives the specifications of the whole product and then leaves the development team alone until the final demo. Everyone works under the illusion that if one spends a lot of time writing the specifications in the beginning, they will be detailed enough to eliminate any questions during the development phase. Obviously, this utopian thinking had never worked, and without a customer on site, the development team resolved any questions that arose on their own, which was neither what client expected. Moreover, because the final users were never involved in the process, the chances that the product will be used and embraced by the targeted public were there low. The hero also noticed that the team members worked in bubbles created by the witch of specialization. So, for example, developers created the pieces of software and then gave them to QA people to make sure that it would be ready to go into production. In cases where it was not good enough for release, the software went back and forth between developers and QA people and developers. So the whole process was extremely long, messy, and completely inefficient. Nobody felt himself responsible for the quality of the software. Developers blamed the QA people blamed developers, and in a rare show of unity, everyone blamed the customer. The quality of the product was evaluated only with external properties like tests, documentation, but nobody paid a lot of attention to the quality of the code itself. And in the short term, that was no problem, but in the long run, poor code slowed the evolution of the software. And every new feature took much more time to implement. So the curve depicting the dependency between time and cost of change grew exponentially. It was difficult to recognize being outside of the code, and the curse of specialization didn't help because there were some developers dedicated to specific parts of software, and the bus factor, the risk of losing a key developer by being hit by a bus, only worsened this curve growth. So all these bewitched elements created a situation where the product was neither ready for the user, and neither the customer nor the product team had visibility on the ultimate product delivery date. So what did our hero propose in such a catastrophic situation? He proposed to throw out the existing code and write the software from scratch, following his magical approach. A year later, they celebrated their first delivery. The magic approach was extreme programming. The hero was Kent Beck and the company Chrysler Corporation. So it was a real story. And what is that magical approach, extreme programming? So extreme programming is a framework that defines several practices applied on different levels of organizations. Practices related to programming are depicted in the center circle. Practices related to internal collaboration lie on the middle circle, and practices related to product management and relationships with customer lie on the most external circle. These practices were not invented by Kent Beck, but he suggested to push these practices to the extreme in order to make the most of them. For example, we know that it's important to write automation tests for our code, but instead of waiting for days while QA people write and run tests for us, developers should assume responsibility for the quality of their code and write the tests even before the code is developed. We also recognize that the code review is a good practice. So let's push it at its extreme too by coding in pairs. This will enhance another practice, collective code ownership, thereby reducing the buzz factor and raising the overall quality of the code. So we understand that to give better visibility to a customer, we should keep him informed about the project's progress. To do that, the team yields and shares small functional releases on a regular and frequent basis, and each release is discussed with the customer, who suggests the features of the next release based on the previous one. So it is possible to do each of these practices in isolation, but some practices reinforce and encourage the others, so they are more powerful when done in conjunction. And what about data science? Are data science projects different from the traditional software projects? So the most important difference arises from the fact that traditional software relies on deterministic processes and machine learning software on probabilistic ones. So in traditional software, we hard code the rules that process the input data. So in that way, we can, or at least we should, anticipate different data inputs. So the rules of the software will not be influenced by the data changes. But in machine learning, as you all know, the rules are created by data. We collect the input and output examples for our training data sets, and with different machine learning algorithms, we create the rules called models. Without bringing a lot of attention to the engineering quality of the whole system all throughout the development process, data-driven rules can be a source for the future bugs and regressions that are tricky to find and fix. The experimentational approach typical for data science workflow doesn't ease this task, generating data experimental paths and pipeline jungles that are difficult and costly to manage. The machine learning systems are often evaluated by external factors like accuracy of the predictions, speed of the inference, or training, but rarely by the maintainability or evolvability of the code behind the model. And this complexity, coupled with the lack of attention to internal quality, generates technical debt that is much more challenging to deal with compared to the technical debt of traditional software. While creating and improving machine learning system, data scientists spend a lot of time prototyping. They research and benchmark different algorithms, their hyperparameters, etc. And it can take an infinite amount of time for the sake of, say, 0.001% of improvement that ultimately could be not even useful for the final user. And one thing is to prototype the solution. Another thing is to put it into production. And according to the VentureBeat article, 87% of data science projects never make it into production. So under these circumstances, it's very difficult or sometimes even impossible to say when a machine learning system will be released. A part of the problem resides in the isolation of data scientists. The lack of collaboration between different team members and stakeholders results in silos of data, knowledge, and skills. This gap ends up with the data and code going back and forth between data engineers and data scientists and software engineers, all with everyone speaking different languages. So we can witness here the same problem of eternal bug passing and blaming we saw at the Chrysler Corporation project. There are often customer doesn't understand what data scientists are doing and how it can impact the business. Since artificial intelligence, AI, become a buzzword mandatory in every modern product to be credible and marketable, the business people often think that investing in AI is enough to miraculously transform the data they have into valuable products. So we can see that all the bewitched links that Ken Beck noticed at Chrysler are present in machine learning products and even worsened by their data-driven nature. But don't worry, extreme data science inspired by extreme programming can change the game. From the point of view of extreme data science as well as extreme programming, the success of the project depends on the collective effort. That's why successful collaboration plays a key role in the win of the game. So what we have to do to be able to collaborate efficiently? First of all, speak the same language. And our first practice suggests using metaphors instead of special technical terms so you can explain your system to all stakeholders of the project. In my previous startup, Tableau, we used neural networks for click prediction, but most non-data scientists had no idea what a neural network was and what we as data scientists were doing. So we organized a workshop where the data scientists worked together with front-end developers to create the posters that demystify machine learning by using metaphors. These posters were much clearer for our whole team than the presentations or posters prepared exclusively by data scientists. And we all know that it can be very challenging to avoid technical terms because the concepts that are obvious for data scientists often break the minds of non-data scientists. So the metaphor created by a whole team turns out to be a really powerful tool to understand each other. And the metaphors drive us to another practice, user stories. User stories should fully describe the functionality of the product, but stay understandable for the customer. And this is the important point because we know that a customer doesn't precisely define the problem he wants to solve with machine learning. And it's interesting that such stories can be used to describe a wide variety of requirements, not only functional, but also technical ones. So if the customer must state a problem with an epic story, a large body of work, and then break that down into simple problems described by user stories, it wipes away a lot of uncertainty that helps data scientists to start work efficiently. The problem statement that is broken into smaller user stories also helps to prioritize the work, and this brings us to another practice, frequent releases. It consists of releasing the minimum valuable product quickly and then enriching it with more functionalities by making small and incremental updates. So it allows us to give better visibility to customers, receive their feedback, monitor how the solution works in production, and detect bugs early and easier. The necessity to release a minimal valuable product quickly will inevitably limit the choice of solutions we want to start with. And it's rather good news because instead of choosing challenging but very complex and resource-consuming solutions like deep neural networks, we will start with simpler ones like linear regressions. And these simple solutions could be useful immediately for our users and give us valuable feedback and ideas and baseline for further directions and research. It goes along with another important practice, simple design or simplicity. The best solution is the simplest one that works. Moreover, we should create code only for the user stories that we are implementing currently without over-engineering it. For example, your company creates electronic components for different electrical equipment. And you have the epic that tells you to detect the anomalies given the consumption of hot water tanks. But you think it's a good idea to make it generic and be suitable for any kind of device, not only hot water tanks. And in this case, you run a great risk to spend a lot of time trying to create a generic solution while there is no need for it at all. In the meantime, you lose your customers who will kid you for your competitor who is less ambitious but does exactly what your customer needs. But you can say me, what if several months later your customer asks you to develop the anomalies detection for another equipment? In this case, the refactoring practice gives you an opportunity to come back to your previous design and remove the outdated or not working parts without any regret or risk. At a different time, I organized a workshop at my current company, Comwatt, to implement a whole team practice. So the workshop consisted of 3 steps. During the first step, I explained to my entire Comwatt team, consisting of developers, product people, energy engineers, the different data science fields using metaphors. For the second step, I left them a poster that had 3 columns corresponding to 3 data science fields I presented. I asked everyone to find use cases related to our company business that could be solved by the methods of the respective data science fields. Primarily, it gave me feedback on how well my colleagues understood the metaphors. And secondly, it gave me an opportunity to get it to the third step. During the third step, we evaluated the use cases with technical complexity and product value criteria. And then we had a long discussion where we analyzed the result in order to separate science fiction from reality. It helped us understand the business values of different use cases, and at the same time, it gave everyone a better understanding of machine learning opportunities and also limits. This kind of collaboration involving all the stakeholders is much needed on a regular basis, but it's also very important that data scientists work closely with the end users to understand the business requirements clearly. At Tabmo, we had a product where our end users, advertisement ops, wanted a tool to find the best configuration of the ads campaign. Firstly, we thought of a quite complex algorithmic solution, and using metaphors, we presented the benefits of this solution to our advertisement ops. We were a little bit disappointed because it turned out that they didn't care at all about the metrics and benefits we thought would be important for them. So finally, we abandoned our first complex solution and we came up with a very simple SQL query that resolved their problem. And this workshop saved us an enormous amount of time and resources that otherwise would have been spent on a solution that would certainly be interesting to work on, but not useful at all for our end users. Another XP practice that accompanies the whole team approach is pair programming. Pair programming consists of 2 colleagues sharing a single workstation, one typing the code, the other giving him indications. They switch their roles frequently during the session. And in my opinion, the pair programming that involves a developer and data scientist is even more valuable, as each one has a different background and approach to solve the problem. So it eases the transfer of skills and dramatically increases the quality of code. The pair programming requires the respect of another practice, coding standards. Suppose developers and data scientists are agreed upon a set of rules such as code structuring, naming conventions, error handling, and formatting. In that case, it allows them to focus during the session only on problem solving. And it also makes it easy to understand and maintain the code base by all the team members. This is a very important point because all the team members must understand and maintain the code base, as stated by collective code ownership practice. Developers can and actually should review and update code created by data scientists and vice versa. This avoids blaming one another, eliminating scenarios like if this module is not working, it's because of data scientists or it's because of developers. Instead, it encourages cooperation, empathy, and new ideas from different perspectives. As I said in the beginning, the fundamental difference between data science software and a traditional one lies in the fact that in data science, data input changes can impact the rules, and the rules in turn impacts the outputs. For that reason, it can be challenging to write the test before writing the code of some parts of the machine learning systems, but it's still desirable when it is possible. Nevertheless, to avoid bugs and regressions, it's not sufficient anymore to test only code. We also have to test the input data properties and the model performance. It's especially important because the machine learning bugs can't be silent. The user may not even realize the problem with prediction. So we have to integrate the tests of model performance, data properties, along with the casual unit tests of code in the continuous integration pipeline, which is another XP practice. I found it especially useful given the complexity of machine learning systems. Imagine you had a team of several people with each one working on a different part of the machine learning system. For example, one is working on the feature engineering pipeline, another one is working on neural network architecture, and the third one is working on optimizing speed of inference. Integrating their work continuously ensures that everyone is working toward the same goal, and the work of one person is not invalidating the work of others. So all these practices were not intended to be applied in a mechanical manner because they are not an end in itself, but they help to favorably improve a team's efficiency with respect to the values of extreme programming, communication, simplicity, feedback, and courage. In my opinion, courage is the most important one because you need courage to take responsibility for a code you haven't written. And you need courage to expose your vulnerabilities and lack of your knowledge during the pair programming sessions. You need courage to choose a solution that is less interesting and challenging, but ensures an early release. And you need courage to keep the process fully transparent by frequently communicating with customers and users. And most importantly, you need courage to trust a new extreme methodology and try it with your team. In my opinion, the effort is worth it, and I hope I gave you a good idea of how useful extreme data science could be and why XP programming practices are, in my opinion, even more critical to apply in the data science context. So that brings us to the end. Thank you very much for your attention, and I'd like also to thank my mother who did all this beautiful watercolor illustrations for this presentation, and special thanks to the organizers for this opportunity and a whole event.